In a previous video, we talked about how a balanced chemical equation represents the mole-to-mole ratio of the species in the equation. The only issue is that when we do experiments, we don't measure things in units of moles. We typically measure masses of compounds, usually in units of grams. So if we want to calculate how much reactant we will need or how much product we will make, we're going to need to convert mass to moles and moles to mass to be able to answer our questions. The good thing is we already know how to do that. All we need is to use our molar masses to make that conversion. So this solution map shows how we will convert between the mass of one species to the mass of another species. So let's say you're given the mass of one species, call it species A, and we're asked to find the mass of another species, call it species B. First, you're going to have to convert the mass of A to the moles of A. And you're going to need to use the molar mass of A to do that. After that, you're going to need the balance equation and the coefficients of A and B in the equation to convert the moles of A to the moles of B. Lastly, you can convert the moles of B to the mass of B using the molar mass of B. So here's an example. Let's say we're asked to calculate the mass of CO2 produced by the combustion of 5.0 times 10 to the second grams or 500 grams of octane, which has a formula of C8H18. Now, octane is a component of gasoline that we use in our cars. So this problem is a practical one if you're concerned about the amount of CO2, which is a greenhouse gas that's emitted by cars that use gasoline. So in this case, we must first write the equations for the combustion of octane. Now the equation is given to you here, but you can also write and balance it on your own using the knowledge you have from watching the video on balancing and reactions. The balance equation tells us that 2 moles of octane will produce 16 moles of CO2. But because what we're given is the mass of octane, we first have to convert the mass of octane to the moles of octane before we can find out how much CO2 we're making. This map here shows our conversion. To convert the mass of octane to the moles of octane, we will need the molar mass of octane, which you can calculate in the periodic table to be 114.3 grams per mole. So the first step here is to divide 500 grams of octane by 114.3 grams per mole, and dividing, of course, is the same as multiplying by the inverse, so that's what we see in this first step right here. However, once you get the moles of octane, we're going to need to go further before we obtain the mass of CO2. So the moles of octane has to be changed into the moles of CO2. And to do that, we're going to use the stoichiometric relationship between octane and CO2, which is 2 octanes and 16 CO2 in units of moles, and that's what we do here. Once you make that multiplication, now your answer is in units of moles of CO2. So we need to do one more step to convert that to the mass of CO2. We multiply that by the molar mass of CO2, which in the periodic table you will find to be 44.01 grams per mole. So that will give us our final answer of 1.5 times 10 to the third grams of CO2. All right, let me show you an example of how to do this mass-to-mass conversion using the solution pathway that we just talked about. So I'm going to work on this example where it says you have a gas NO2 that's a component of exhaust gases generated by internal combustion engine, which is like your car, for example, and then it reacts with oxygen and water to produce nitric acid. There's a typo there, it should say nitric acid. Assuming that there's more than enough of the other reactants, how much HNO3, which is nitric acid in kilogram, forms from 1.5 times 10 to the third kilograms of the NO2 pollutant. So as I said in the previous videos as well as in this one of the things you need to do first is start with a balance equation. So we're going to start by writing all the reactants and products. It says we start with NO2, reacts with oxygen gas, reacts with water to produce HNO3. Now, it might seem kind of difficult to do this, but you remember what I said is you want to leave your free element to the last
So that means leaving your oxygen in the last step of balancing. So we can start with all the other ones first. We see that we have 2 hydrogen right here. So that would mean that I'm going to need to have 2 hydrogens here. And once I do that, then these 2 are off limits. I'm not going to touch them anymore. I notice that now I have 2 nitrogen because of the 2 that I put there. That requires me to put a 2 here. And so that would also make this one off limit because now the 2 nitrogen is already balanced. So we're left with the last element to balance, which is our oxygen. And if we count the number of oxygens we have, on this side we have 6 oxygen. On this side, we have 4 oxygen and 1 oxygen. So that means that to balance this out, I'm going to need 1 oxygen coming out from here. Since I already have 2 oxygens in the formula, the only way I can make it into 1 would be to multiply it by a half. And of course, that would give us our balance equation, but we can't really have a fractional coefficient. So what I'm going to do is take the entire equation and multiply it by 2 to give me this new equation. 4NO2 plus oxygen plus 2H2O forming 4HNO3. That's my balance equation. Now I need to do my stoichiometry calculations to take it from the mass of NO2 to the mass of nitric acid. And we start with the mass of NO2, which is 1.5 times 10 to the third kilogram. Now, the first thing you might want to do is just convert this to grams because we would end up having to use molar mass, and molar mass is expressed in grams. Those of you who are quick at this, you can do the conversion in your head and write 1.5 times 10 to the 6 grams. But if you're not confident, you can do this conversion that I just wrote out. And the next thing is, remember, you need to take it to the number of moles because the equation itself is a mole-to-mole relationship. So for the number of moles, I'm going to need the molar mass of NO2, which happens to be 46.0055 grams per mole. Now I'm writing it the inverse of the molar mass because I want to cancel out the grams. And that's why, as I said in earlier part of this video, you're really dividing by the molar mass, but if you write it as a multiplication, it will be the inverse of the molar mass. Now, once I do that, the unit I have right now is the moles of NO2. Now I need to do a conversion between the moles of NO2, which I should write at the bottom, or denominator, since I want to cancel it with this guy. And I want to take it to the moles of HNO3. That was my other species that I'm interested in. And the numbers I need to put in front would be the numbers that come directly from the balance equation. So in the balance equation, there's 4 moles of HNO3 for 4 moles of NO2. So I'm going to put those 2 numbers there. Once I have that, my last step is to convert the moles of HNO3, I want to cancel that out, and to the grams of HNO3. And as you can see, given that unit, grams per mole, that's just the molar mass of HNO3, which ends up being 63.01 grams per mole. If I multiply all this across, I end up getting 2.1 times 10 to the 6 grams of HNO3. The question itself asks me to find the mass in kilograms. So the last step is to convert this back to kilogram. And that would mean my answer would be 2.1 times 10 to the third kilogram of HNO3.